Good evening.
Добрый день. Добрый вечер, Лена.
Добрый вечер.
Добрый вечер.
Привет.
Всем здравствуйте.
Hi, Michael.
Наташа, добрый вечер.
Мгм.
Да. Здравствуйте всем.
Здравствуйте.
Hello, Matthias. So there is at least one non-Russian speaker present. Good. So we have 3 minutes more. Наташа, я могу приготовить пока?
Да, все можете.
Так, значит, пытаюсь это сделать.
Добрый вечер.
Добрый вечер.
Добрый вечер.
Здравствуйте, Игорь.
Получилось ли у меня?
Да, все видно.
Отлично. Привет, Игорь.
Понятно.
So now it's time to start. Hello, everybody. you see the title of my talk, and then before we turn to the plan, please look at the art object, the mathematical meaning of which is at the moment perhaps not quite clear, but from the point of view of visualizing the objects we are going to speak about, it is the central one. Unfortunately, I was unable to cover by pictures everything that is related to the mathematical content, but I did it in several cases. So this is the plan. As you see, the question mark near the point 5 means that the calculation of the corresponding Belly pair is, so to say, in progress. However, I'll share some results. So, as the zero slide of my talk contains just some philosophy in the attempt to put this material in more general mathematical context. The talk is devoted to quite a particular object. And here I give two examples of other objects that illustrate the general principle, the relations between various mathematical theories, the part of mathematics that, according to my teacher Shafarevich, is the most interesting in the whole mathematics, sometimes is better understood in terms of particular objects than in terms of general theories. So the two examples are the Klein quartic, about which and about whose relations with the main topics of our seminar we spoke a lot, and the other example is very well known. The monster created lots of conjectures and considerations, and to the best of my knowledge, to the time there is no really popular exposition of the whole theorem. Therefore, and it is just of the signs that we don't understand everything about monster, and maybe even about the simple explanation of its existence. And now in the last paragraph of this slide, I quote a person I don't know, but it lists several topics in mathematics that are related to it, like finite projective planes, latent squares, skew-Hadamard matrices, and so on. It is just the existence statement. We consider only those that are traditional for our seminar, plus octonions that are by no means traditional. And maybe I just share some random dreams about relating what we are usually doing with octonions. since we know now that their algebra is best understood in terms of just one single descendant form. So the next slide is the beginning. It is just the traditional topic. Only preparing to this talk, I learned that the author of this triangulation is Möbius, what I knew before, and would like to inform everybody that the contributions of Möbius to mathematics are by no means bounded by, by the main object bearing his name, Möbius band. And I have to confess that though it is important, say, in the pedagogical activities, since it gives the simplest non-trivial example of the actual calculating of simplicial homologies, I never liked it, as I state here. I don't find it is nice. It is not really easy to understand that it contains exactly 7 vertices. Non-memorable, the statement that it is memorable is again kind of subjective. I am unable to memorize this picture, unlike the other. Sorry for suggesting a small and colored copy of the 9 triangulation, but this is just the 3 by 3 squares parted into by the parallel diagonals, and of course it is assumed that the opposite sides of this square are identified, and it is easy to work with. It is easy to give names to its vertices and edges, and in my pedagogical activities I used rather this one. Everything changed when I met the paper by this Savarnek that I'll quote. And now we have just another vertex. Yes, sorry, the last claim is that it needs some efforts to see the graph K7 embedded in this torus, and I suggest some explanation. Well, from the point, from some other points of view, for example, considering the nerves of the coverings that are small extensions of the cells. The hexagon works much better than the square with the opposite sides identified, just because its nerves, the nerve of such a standard covering is simply homeomorphic to the additional, to the initial torus. So, and now a couple of slides for just the history. As you see, I quote some very recent paper. So instead of, well, taking bits of information from somewhere, I just copy the full parts of it. So perhaps I should not just read what you see on the screen, but highlight the main points, which is the Hewood graph that is a pair of the complete K7 graph in the story we are going to consider, is in some sense central in several strands of developing mathematics. So here I have found some details about the concrete history that we'll see on the next slide about many false proof and false counterexamples. One of them, as we see, was famous and was believed for about 10 years. Then 1890 happened, and perhaps the main hero of today's talk, Percy Hewitt, has found a gap, and then proved the weaker theorem, and it turned out that there are three theorems called some number colored theorem. The most famous is the four-color theorem. Hewitt himself proved the weaker five-color theorem, and then he established this number. He considered the covering of the surfaces of higher genera and has introduced this nice number, nice function of the genus G, and it is important to plug G equals 1 there, just to see that this number is exactly 7, and then he would show that he would go to to study this number in the simplest case was to show that it is tight, as the author see. So one needs constructing the 7, the embedding of coloring the torus in 7 colors. It is not exactly equivalent to the problems of embeddings, but as we know from our activities, it is closely related. A funny detail of a historical detail is that the real descent that the Hewitt has suggested is really ugly. I was unable to reproduce it. Just suffice to say that he realized this embedding in the annually separated in some terrible curved figures. So, is it correct? Yes, and sorry, I don't remember when is it time, maybe just now, to say a couple of words about this very recent paper. I know nothing about the authors, but the main content of this paper is a kind of generalization of the Hewitt graph. Though they do not consider it from the point of view of descent d'enfant, I'm sure that they are these generalizations they consider are interesting and important for our theory. So perhaps the history stops here, and there is just the mention about 7-color theorem again. Yes, so as we see, the tightness of the Hewitt function is quite a recent result. Some of the participants were already alive when it was proved. And as for the inspiration of the beautiful math art works, it just illustrates again that the same mathematical objects can be, descend and fun can be drawn in some ugly way, like the initial minimal triangulation of torus and the Hewitt initial picture that unfortunately is hidden from the list of participants. But after some work and thought, they can be transformed in the most beautiful pictures that I hope to illustrate following this Ceballos Doolittle. Now let's turn to our language, and instead of Hewitt graph that is famous for its embedding into torus, just rename it into the Hewitt descent, and we'll just consider, well, we can count count its elements and see that this is the problem of realizing this very symmetric passport. Yes, now I see that only in the final sentence of this slide I mention these generalizations that I highly recommend. I myself only looked through it. Now let us describe the main construction of it, perhaps in some details, just to be sure that we are working with a very concrete object. So, unfortunately, unlike the name I for the imaginary unit, there is no really standard name for the cubic root of 1. They use zeta, omega, and, well, I suggest rho not to have wrong connotations. Now we introduce the ring, the very well-known ring of Eisenstein numbers. This ring is, of course, parallel to the ring of Gaussian numbers, but as I understood preparing this talk, it is much more difficult to work with its elements in a visualizable form. So I've tried to do that, as you perhaps see, and maybe we should mention another historical moment related to these numbers. As perhaps many of you know, the last Fermat theorem in the case of power 3, the statement that no, the sum of two cubes cannot be a cube, meaning the cube of a positive natural number, caused some discussions of whether Euler has proved it. But in fact, what Euler meant was the unique factorization in the field of Eisenstein numbers. The approach was, that is supposedly goes back to Fermat, and for which he had not enough place on his margins, was related just to the factorization of the sum of cubes over this ring. And now it is very well known that it is the ring of principal ideals, and what we are doing is considering just one of, here we are introducing this ring in the general algebraic way. Now I'd like to repeat that it is the principal ideal domain. So any ideal we could consider in it. Maybe I should remind what I didn't draw here, that the ideals in Gaussian numbers are very easy to draw, see, using the graph papers. It is nothing but the skew square lattices. And the ideals here are some regular subgroups of the additive group of the corresponding ideal. So I did my best to make it visualizable. I'm not sure how clear it is. So as I write, the colors will be explained later on. And now drawing 0. So what you see is the colored hexagon tessellation of the complex plane. Let's emphasize it, that our geometry takes place in the complex line, and our abstract ring of Eisenstein numbers is considered as the subring of the complex numbers. So just to give the origin, I mark 0, to give the scale, I mark 2, and then I did my best to draw 2 minus rho. It is here. Well, rho is somewhere, I'm unable to draw everything, somewhere where I point now. And this is 2 minus rho. Another funny detail that perhaps has to be mentioned, in the ring of Eisenstein numbers, there are no canonical choice of the generators of ideals, because as even over integers, where the generator of ideal is defined up to a sign, here the group of units is the group of square roots of order 6, and so instead of in formulas, this ideal is defined as the one defined by this point, but with the same motivation, we could choose this or this or this or this. It is not defined canonically. So what is supposed to be seen here is just the embedding of some free abelian group of rank 2, about which again we can say that it doesn't have natural generators, and it is somehow regularly embedded into the complex numbers. I would perhaps even prefer to say that this abstract group of rank 2 is embedded into the additive group of complex numbers. So our object is nothing but the study of the factor of the additive group of complex lines, by the group that is drawn here in the rather thick black points with 0, the thickest one, and 2, the small one, that just scales our picture. So this is what we do for what I was trying to contribute for the visualization. Now there is some algebra. Now we remember that we work indeed not just with the abelian groups, but with the rings, and so the factor over the prime ideal, the maximum ideal, is the finite field, and at least for me, it is by no means easy to identify this field. It turns out to be the field of 7 elements, and this field is in the kernel of all the mathematics that we discuss and are going to discuss. Now we have the small problem of naming the elements of F7. By the way, if on this picture I would use the natural element like 1, 2, 3, 5, 6, 7, then it would be impossible to understand because they would mix with the natural numbers. So we choose the appropriate names for them, and they are just the names of the colors. By the way, again, during this preparation, I learned something I didn't know before. The number Isaac Newton was the first who has analyzed the rainbow, and since the boundary between the colors is not really defined, really not obvious, and the colors change, are transformed into others, Newton just had the idea that there should be exactly 7 of them, and the motivation of this idea had nothing to do with color, was motivated by music, because he wanted that the colors to correspond the musical gamma. Sorry, I don't know the English word. I mention it just because maybe in somebody's imagination this picture can be played somehow. Maybe I did not emphasize what I should, that the rainbow colors can be traced in several ways. One of them will be used, and it is the Voronoi Dirichlet fundamental domain, just consisting of the 6 hexagon bounding the central one, but we can see as well the whole line of the colors, so to say, some rainbow going this way or going that way, or anyhow. So the the set of possible associations and intuitions is perhaps not exhausted by a simple formal study of it. So here I just remind the names of the rainbow colors and draw them. And now it is not really difficult to calculate the correspondence. This is what is done here, and well, the result is formulated somewhere below. I mean, the algebraic representation of the Dirichlet-Voronoi domain of it. So now a bit of more quotation. This is what I was just trying to say, that this is the 7 elements that correspond the representatives. Sorry, he refers, 7 neck refers to some other picture, but may I show it again? So one can check that these 6 elements have a more regular listing like this, the symmetric one with respect to 0. So this is again just about the picture. And now let us try to turn to our understanding of the embedded graphs. So I believe that most part of us is used to the geographical understanding of the graph, of the Sendamfang, in which the we use the kind of political geometry. We consider the surface as the planet and the graph as the set of boundaries between the planets. And here we have a funny political geometry, in some sense the smallest, with the 7 hexagonal countries, that by Hewitt, every country is the neighbor of every other. It just tells us that the dual graph, the graph of the, say, the roads from the capital to all the neighboring capital, is the complete graph K7. And now let us do our standard identifications. So the vertices of the complete graph are now identified with the colors, and at the same time with the elements of the field of 7 elements. Now, as for the directed edges of them, they are defined by the pairs of different vertices. So there is the Cartesian square of it minus diagonal. And there is a very important mapping from it to the multiplicative group, just associating to the directed edge of our graph the difference that lies in the multiplicative group of the field. And now here is the full combinatorics of it. I don't believe that it can be really understood without checking everything. And by the way, I don't know how to represent it in the static picture. It would be rather easy to, well, create some movie with, the rounding the point, the going around the vertices. But, skipping the details, let us just formulate the main question. How do we transform a graph, in this case, the graph K7? Sorry. In fact, we are working with a dual to it. So it is the graph of the vertices of the corresponding tree. The graph is trivalent. And so to define its embedding into any surface in terms of graph itself, we have to choose one of the two cyclic orders on the set of edges incident to a fixed graph. And it turns out maybe there is some advanced method. I just checked it by, the detailed identifications, again, for which we need something like the picture I have showed. And it turned out that the corresponding cyclic order, that is the action of the three-element group on the set of edges incident to a fixed vertex, is just nothing but the multiplication over the subgroup of order 3 that we have. We can just exploiting the field of 7 elements. I mean, we actually use the standard theorem that the multiplicative group of any finite field is cyclic, and here we have the cyclic group of order 6 and subgroup of index 2 of them that consists of the squares in the multiplicative group. So the squares of the field of 7 elements determine completely the structure of over the complete graph K7 that turns it into the descent, or some people like to mention ribbon graphs here. So that's what I was going to say about the descent. And now we turn to the topic that is kind of exotic in our seminar. I don't think that, well, it is mandatory for a usual mathematician to know, just to know that octonions do exist. So maybe I say a few words about them. Again, the history is very interesting, but it is, it is the continuation of the route from real numbers to complex numbers, then to non-commutative algebra of quaternions, and then even to non-associative algebra of octonions. However, they are remarkable, and mathematicians stop here because all of them are division algebras. Every non-zero element has the multiplicative inverse. As for the octonions, it has some property and perhaps is defined by it, that it is as close to being associative as possible. It means that any two elements of it generate the associative algebra, namely the quaternions. Now what we are doing, so the main point that is fantastic for me, really fantastic, is that the observation perhaps of this seven neck, again unknown to me, and I don't know from which country he comes. So that the complicated rule of multiplication in octonions becomes almost trivial if we use the Hayward graph. So the recipe is formulated here on the half of the slide. Well, maybe try to somehow visualize the space of octonions. So our colors are the analogs of the imaginary dimension in the complex numbers, and I, and the three imaginary dimensions in the quaternions. Traditionally, since the time of Hamilton, denoted by IJK. Here, instead of three, the basic imaginary elements, we have 7 of them, and we are identifying them with the colors, but perhaps most basically not just with the colors or with the musical sounds, but with the hexagons on the Hayward descendant fun, either on itself or on the universal cover that we have seen, and that is the colored tessellated, complex tessellated by the regular hexagons. And now here is what is written here. I'm not sure that all the words are necessary, and we just repeat it. I take the quotation literally, almost literally. My notations are a bit different from seven neck. Here we just repeat what we have, and denote the basic elements in a more boring way, simply by the indices of this, of the field of 7 elements. And now, the 7 elements correspond to the imaginary units, and we just define all of them being kind of imaginary units, just with the simplest multiplication rule that can be drawn. Sorry for my not drawing it. Again, it's much better understood understood dynamically. Cyclically ordered hexagons around a circled vertex. I'm not even sure that I understand the word circled here, but what I really understand is that we take a vertex of our embedded graph and go contrary clockwise around the point of their common boundary, and all these walks, trips through 3 countries, crossing three boundaries define completely the multiplication table. So I don't know the emotions of other participants, but to me, this simplicity and the application of the true application of the sense, in fact, of just one remarkable sense, to me, it seems fantastic. That's why I'm giving this talk now. So now, as I warned you, the subject of Belly pair is with a question mark because it is well, for me, it is not completely easy. It is possible that somebody else could do it during, well, one evening or 1 hour or several minutes. So sorry, not lock, of course, the elliptic curve, but just by the picture of the factorization of the whole tessellation, colored tessellation over F7, we get the 7 isogeny, and we know very well what curve it covers. Of course, the curve with the simplest multiplication, with the automorphism group of order 3. I didn't write here what perhaps everybody knows, that the curve with a J invariant 0. So we have a task to find one of its 7 isogenies. And of course, our Belly pair is going to be compositionally reducible. And, well, its way to P1 goes through the standard Belly function on the curve with J invariant 0. So instead, but some very special trick, I have realized so the definition of this modular curve x sub 1 of 7 is simple. It is just the set of isomorphic classes of elliptic curves. Well, when we are saying elliptic curves, perhaps we mean with a marked point that is a neutral element. Sometimes it is more preferable to think about it as about tori with 2 marked points with such a condition that their difference has order 7 in the additive group of the torus. And so this is x sub 1 is the standard notation for the corresponding modular curve. It is easy to find out that this curve is rational, but by no means easy for me, and well, just Googling something to find its explicit parameterization. Because, well, the modular curves as the part of mathematics are in a very deep connection with the theory of modular forms, and this is one of the most, to my taste, it is one of the most complicated theories in modern mathematics, and it is full of true formulas, but they are very long and complicated. So instead, I have found some parameterization by hands, So what is the origin of such a maybe strange parameterization? I write the elliptic curve in such a form that it has, besides the infinite points, it has a marked point where x is 0 and y is 1. So I parameterize all the curves that for which this point is the point of order 7. And well, this formula is nasty, I would say, but I think that the cycles themselves are nice enough, at least working with different parameterization. We come to the formulas that are terribly long, and these ones are short and well factorized, and we see immediately some singular values of the parameter t. So I just give the 3 points of the cycle, because the 7th cycle then go back and return. It is better to understand it with a picture, with a standard picture of the cubic curve in the Weierstrass form, when where we distinguish a point with the number 1, and it turns out that the 6th iteration is minus this point with the opposite sign of the ordinate. Therefore, we have 6 points of the cycle, but the 1st and the 6th are mutually inverse, and adding them, we get, as we should, to the neutral element, the infinity. So the only thing that remains is to find this t, and it is not so well. I had now I have serious reasons to believe that I know it conjecturally as some cubic irrationality, again some element of the field of the Eisenstein field. And I have explicit formula for them, but these cubic irrationalities are terribly complicated, and it is by no means obvious that they belong to this field. They are just some solutions of cubic equation with integer, with enormous integer equations. But studying it, we see that they really live in this cubic field. So it again tells us that my parameterization is not very good, though the dynamics is quite clear. And for the time being, I'm not really sure how to improve it. And now the last thing I do, just to claim that the problem is partially solved, that I have some partial results. And it is related with the calculation of the J invariant of the family. So, of course, these terrible polynomials in the that are in the numerators say nothing. This they do not factorize over Q. I think that they factorize maybe in the Eisenstein number, but my maple does not doing it automatically, and perhaps well, there are some more advanced systems that would help it to factorize. However, it has exactly the same shape as desired, as in the simplest cases. So I mean, J behaves exactly like the Billy function on the base of this family. I mean just the shapes of it. So there is no good news concerning these numerators. And I think before the attentive working for them, I'm going to try to find the better parameterization that would, however, keep the nice 7 cycles of it. But as for the denominator, there is some sign of the well, correct direction. So here is the denominator. First of all, it is factorized, and there is some nasty polynomial that for the time being have no meaning for me. But what is really nice is that these singular points that we have met, 3/23 and 1/21, of course, they should be in the denominator, but I can say nothing about the, I'm not really sure. I'm afraid that I'm not used to it. I think that here the power is 7 again. Yes, I'm almost sure that the power here is 7. And this is, of course, the sign that we have again some, well, analog of the Adrianov's pharaoh, and that the desired he would descend can be extracted from this family. But well, one of the advantages of the what I call methods of free families is that we have some complicated free set of family of free pairs depending on the rational parameter t and on the Riemann sphere on which the t is varying. We have some descents, the combinatorics of which can be extracted from these formulas, and the desired t sits in just one vertex of the corresponding descent, and perhaps something interesting sits in the other descents. So I have occupied exactly the hour besides 1 minute, and unfortunately I have to stop here. I was going, and I have promised to consider the simpler cases. I believe that they are considered in the literature, maybe even by some of the people who are here. So thank you for your attention. The list of quotations is large enough and is available. So that's it. Thank you again. Any questions or comments?
Well, George, you referred to the design as if it was a single design, but really it's a chiral pair of design. So if, for example, you're going to use this design in order to explain the multiplication of octonions, then you have to make an arbitrary choice of which of this chiral pair. They differ.
Sorry, Garrett. First of all, hello, nice to meet you. And could you please repeat a pair of what do I have?
Well, you referred to this design as if it was just a unique design, but in fact, there are two designs. They form a chiral pair, and they differ by a choice of a generator of the cyclic group of order 6. Now, this non-uniqueness could pose a little problem if, for example, you use this design in order to explain the multiplication of octonions, then you must make an arbitrary choice of which of this chiral pair you're going to use. And this may cause some non-uniqueness in the multiplication of octonions.
Gareth, thank you very much for this remark. And it clarifies the lack of, say, the natural choice, the lack of rational parameters. So there are, as you say, the chiral part, the chiral pairs of the objects, yes, and you more or less, and the one of the things to do is to realize them geometrically, hopefully by recoloring the whole picture. Perhaps there are some regular way of recoloring them and really consider the pairs of them. So thank you very much. I'll try to take it, to take this remark into account.
One other historical point is
Yes, please.
the idea of using finite fields to describe embeddings of complete graphs goes back to Hefter in the 1890s, and he did it for every
1890, yes.
yeah, he did it for every field of prime order. And then in 1970, Norman Biggs extended this to all prime powers. So for instance, he proved that you get a regular design for a complete graph, Kn, if and only if n is a prime power.
Is it?
Well, thank you for very interesting work, but I wish to remind the English at English, Richard of York gave battle in vain.
Yes, it's a very useful
Каждый охотник
mnemonic.
желает знать, где сидит фазан. Thank you very much.
You're welcome. So, Gareth, is it correct that the historical references that you have mentioned can be found in your papers?
Yes, yes.
And so on. Okay.
Yeah, and in the book with Jürgen Wolfart, there's a section on embeddings of complete graphs, and we work out the field of definition. They're all defined over cyclotomic fields, for example.
Yes, that was my feeling that lots of things were done, and even I have expressed the hope that maybe somebody of those who are here, and so thank you for confirming it. Any other, please, questions or remarks?
I would like to remind that the 7-color picture, 7 colors coloring of the hexagon tessellation is used in the problem of plane chromatic number. If you remember, 7 years ago, object degree proved that plane chromatic number is at least 5. And it's still an open question. What is the correct answer? What is the correct chromatic number of the plane? It is known that it is less than 7 because you can color. It's not greater than 7 because the picture that you have shown just a picture of coloring the plane in 7 colors, such that any 2 points at distance 1 are colored with different colors.
Yes, thank you. Other remarks, please? Okay, then I hope that in some time I'll be able to fill the gaps and then speak about it again. So, best wishes to everybody, and bye.
Thank you, George. Great talk. Thank you.
Thank you.